Swayam Prabha. Digital India. Educated India.
Hello all, welcome to this course on astrochemistry. Now this is the third lecture of this course. So in the last two lectures, I had kind of given you a brief illustration about what astrochemistry was and had also provided the precise meaning of the word astrochemistry, how we basically study the molecules and atoms in space, and followed by that I used the examples of some chemical reactions to highlight how the chemistry happening in space can give us a completely new perspective of chemistry itself, because chemistry happening in space is very different from that happening on Earth. And of course, there are some similarities also. It's not just differences, it's also similarities. For instance, we noted that in space, we can have a reduction reaction alone or an oxidation reaction alone. However, on Earth, it is not just a reduction or oxidation reaction, but it's a redox reaction. That is a combination of reduction and oxidation reactions happening together. So overall, the idea is that we can study astrochemistry to gain new insights about chemistry itself. And not just that, astrochemistry can also give clues about how the molecules responsible for the origin of life could be formed. So in other words, studying astrochemistry gives us a clue about the possible origin of life itself. Please note, I'm carefully using the phrase possible. I never claim that we can understand the origin of life precisely. However, studying astrochemistry gives us more clues, and by connecting it with astrobiology and astrophysics, we get tremendous clues about how life may have formed, which is of course an open-ended topic, which has been discussed tremendously in the scientific literature. We'll take a look into all that. So in today's lecture, in lecture 3, we shall look into the constituents of space and the scope for chemistry that they provide. Okay, so where do we begin with? Now, to begin with, it's an interesting thing, right? It can be a philosophical question. It is often discussed as part of religious discourses. It is often discussed, just as a matter of fact, without even thought. Oh, where did life begin? Where did the universe begin? What happens to time? When did time begin? When did space begin? So these are questions which are common at the realm of intersection of both philosophy and science. Now, in science, we have this subject called as cosmology. Cosmology, which deals with the origin of life itself. Okay, right? Life, and not just life. You can say cosmology more accurately is about the origin of the universe. Okay, right? So cosmology being the study of the origin of the universe, there are certain standard models. So we have some standard models of cosmology which talk about So the standard model of cosmology talks about the possible origin of the universe. So before we actually proceed to understand the constituents of space and how like the different constituents of space give scope for different types of chemistry, we shall first look into very briefly using the idea of the standard models of cosmology as to how exactly the universe originated and how did the elements come about and what that teaches about the type of chemistry that is possible in space. Okay, so we shall look into that right away. So the first question that comes to our mind is, how did time and space begin? This is the very first question, right? I mean, I'm definitely not a know-it-all and I don't have definitive answers. However, very bright minds, exceptionally bright minds, and scholars in physics, astrophysics, astronomy, theoretical physics, high energy particle physics, etc., have been spending a lot of time on this question. And the currently accepted model is what? You all know that, right? It is the Big Bang theory. Now, what does the Big Bang theory say? The Big Bang theory says that both the universe and time, that is space and time, from t equal to 0 began from a sudden expansion from a point. We may even call it to be a very hot point whose temperature was of the order of 10 to the power 32 Kelvin. Now, this is the proposition of the Big Bang theory. It is widely accepted. There are, of course, several variations as to exactly what is the sequence of events after the Big Bang, etc. However, for the past 100 odd years, the Big Bang theory is the most widely accepted theory about the origin of the universe according to the standard model of cosmology. Is it the final word? I'm definitely not saying that. However, it is the currently accepted version, and let us just go with that for this course. So, starting from t equal to 0, space and time begins, followed by the sudden expansion of a very hot point whose temperature is of the order of 10 to the power 32 Kelvin. Now, can you imagine this number, 10 to the power 32? It is larger than even the Avogadro number. The Avogadro number is of the order of 10 to the power 23, right? Even that itself we cannot visualize. Now imagine 10 to the power 32, right? So that is how hot, when it all began. Okay. Now, the question, you might ask me is, okay, I understand that you take this model for granted, but there should be some evidence, right? After all, why should people accept this model? So let us now look into a prominent evidence, okay, right? Salient evidence for the Big Bang theory. I'm just calling it BBT. Okay, right? The evidence, salient evidence for BBT. Now, this comes out, right? The salient evidence for the Big Bang theory came as early as 1925 to 1930, sometime in that period, wherein this prominent scientist Hubble, he observed that galaxies. Now, of course, I have not defined the term galaxy for this course, but from a high school level understanding, what's a galaxy? A galaxy is nothing but a collection of stars, planetary bodies, asteroids, comets, etc., together. Note that we have not talked about any of them in particular. However, we can roughly define a galaxy to be, a collection of celestial bodies. Okay, right? For example, we live in the Milky Way galaxy. This is common high school knowledge, or not even high school knowledge. This is primary school knowledge, correct? So starting with this, right? Starting with the idea of a galaxy, Hubble observed that galaxies are moving further away from us. constantly. Now, what does this tell you? This tells you that the universe is expanding. As galaxies are moving further and further away from us, the universe is obviously expanding, right? It is not contracting. But the next question you should all ask me is, okay, how did Hubble come to this conclusion? How did he know that? After all, did Hubble go to one of these galaxies? Is it even possible to, cross the Milky Way? Forget Milky Way. Can you cross Earth that easily? Correct? So it is not so easy to actually tell how exactly a galaxy is moving further away. Isn't that correct? But hey, here is where, right, fundamental science comes to our rescue. So how did Hubble know that galaxies are moving away? What do you think is the answer? So the answer is Hubble measured starlight's wavelength from a faraway galaxy. The exact details are not pertinent for us, but just understand that. So you can get a spectrum. You can get a spectrum from any star, right? All you need to do is have a telescope and attach a spectroscope. A spectroscope is roughly, like it contains a prism, a grating element, sort of an attachment to a telescope, and with this you can get the wavelength of stars obtained from very different sources, right? Stars which are extremely far away. You can even get their spectrum, and from their spectrum you can get the starlight's wavelength. Are we clear? This is what I mean by obtaining starlight's wavelength. So you can record a spectrum of like very far away celestial bodies, and you can get the spectra, and from that you can get the wavelengths corresponding to specific lines. Okay, right? Now, this is something that as I also explained to you in lecture 1 or lecture 2, I forgot which one, maybe lecture 1, I told you folks that the beginning of astrophysics itself deals with measuring, the spectra of celestial body. So the concept of measuring the lines from the spectra of various celestial bodies was well known by 1900s, and the Hubble's experiment took place approximately around let's say 1925 or 1928 or something like that. Okay, so he measured the wavelength, and he found that the wavelength, which is given the Greek notation lambda, was redshifted. Now, what does it mean by redshifted? What does it mean by redshifted? Well, I'll explain to you. Now, what it means by redshifted is that the lambda of, let's say, let's call it star, okay, right? Lambda of the star coming from a faraway galaxy is, let's say, you can calculate the lambda of the starlight, okay, right? Using the assumption that the star is at rest, right? You can also, don't worry about how exactly this is done. I have not told you that. This is not relevant for our course in particular. However, if you're interested, please contact me and let you know that. So this is the lambda of the star under the assumption that it is at rest. Similarly, you can also calculate the lambda of the star. I'll call it lambda of the star at rest and lambda of the star when it is moving. Now, when lambda Sm is the lambda of star that is moving. So when lambda Sm is greater than lambda Sr, you understand that there is a redshifted line in the spectrum of the star. Please note this idea. Okay, right? So you can measure this. You can measure, the spectra of various stars, and you notice specific lines, and you note that these lines are redshifted. By redshifted, you understand that when the star is at rest, vis-a-vis, like when the star is moving, the wavelength is greater. Now you can ask me, hey, why should the wavelength be greater? Why should it even change, whether it is at rest or whether it is moving? What is the answer to that? The answer is high school physics, or perhaps, like college first year classical mechanics. The answer is discrepancy arises due to relative motion between us. We're talking about relative motion between us and the star. Okay, for example, how many of you have moved in a train? As you go in a train, as another train, right? As another train immediately, comes right next to you, right? We understand that the noise emitted, the noise emitted is much higher when the train is passing towards you. And as the train is passing away from you, the noise emitted actually becomes lower than the actual noise that is. Do you know the name of this effect? What is the name of this effect called? This is called as the Doppler effect. So the same Doppler effect that is applicable to sound waves. When we are discussing about trains moving or people moving relative to each other while they speak, or like the honks of cars, etc., etc., we talk about sound waves. So the Doppler effect is also applicable to light waves. And in addition to including relativistic effects also, because the star may move very fast, right? We notice that the wavelength obtained, just as the frequency of a sound wave changes, right, due to the relative motion between the source and the observer, similarly, the wavelength of light wave also changes when it is at rest, assuming it is at rest, and when it is moving. And we know that it actually is moving, right? Stars are not static objects. Are we clear with that, right? Yeah, so stars are not static objects. So we understand that there is some shift. And when the wavelength of the star, when it is actually moving, is greater than that of the wavelength of the star when it is at rest, we call it redshifted. So based on the redshift, of the starlight, right, which arises due to this fundamental concept called as Doppler effect due to relative motion between any two objects, right, we understand that galaxies move away. So when galaxies are moving away from us, we understand that the universe is expanding. So as the universe is expanding constantly, we have some evidence to probably, put it all together back in time, that, hey, it must have all begun from one particular point. So this is some indirect evidence of the Big Bang theory. Of course, there are lots of details. Researchers are constantly discussing lots and lots of details to be modified about the Big Bang theory. And they talk about various steady states and how the sequence of events in the Big Bang, etc., can be questioned. But the broad idea is that the universe is expanding, which is a known, which can be experimentally observed. And based on this, the Big Bang theory seems to be a credible starting point for the universe based on the standard model of cosmology. Are we good? So with this understanding, we shall proceed further to understand the formation of chemicals. When I say chemicals, hey, this is a chemistry course, right? It's astrochemistry. I'm talking about atoms, elements, molecules, and compounds, etc., etc. And by the way, when did all this happen? When did this Big Bang happen? And from the Big Bang, how much time has passed? Any idea? The accepted version is that from Big Bang until now, approximately 1.38 into 10 to the power 10 years have passed. Okay, right? So this is again based on standard models of cosmology. I'm not going into the calculations intentionally because that would be a huge digression from the content of this course itself. So approximately, this many years have passed since the Big Bang. So you can call that the universe is approximately 13.8 times 10 to the power 9, which is like 13.8 billion years old. That's how old the universe is. for your understanding. Okay, right? Now, from this temperature, what was the temperature I mentioned at the Big Bang? It was 10 to the power 32 Kelvin. Now, all, everything started from here and everything evolved. And when I say everything, I'm talking about all the atoms, molecules, compounds, forms of life, etc., from here as the universe expanded and cooled down. Okay, right? Now, we are particularly concerned with chemistry. And what do we know to be the basis of chemistry? What forms the basis of chemistry? Any idea? Yeah, molecules, atoms, and what are the constituents of an atom? You have the nucleus and the electrons, and what is inside the nucleus? Typically in chemistry, a nucleus is not broken. However, in astrochemistry, the nucleus plays an important role too. So what are the contents of a nucleus? At high school level, yeah, nucleus contains neutrons and protons, correct? Yeah, so the nucleus contains neutrons and protons, right? And we kind of have a picture that, we have a central nucleus and around it we have the electrons. Although, this picture is not to be taken too seriously because of the concept of wave-particle duality in quantum mechanics. I will get to that also in a bit, okay, while I explain how the molecules are detected in space actually, okay. But we kind of have a sense that there are neutrons, electrons, and protons. Let's not worry about the quarks that hold together the neutrons. That is beyond the scope of this course completely, okay, right? That may be more appropriate for a standard, a course on standard model of physics or like high energy particle physics, etc. So when were the neutrons born, when were the electrons born, and when were the protons born? That is the question, we are going to be discussing. So let's say, it is believed, okay, it is believed, and based on some calculations and some experiments in high energy particle physics also, it is believed that 10 to the power minus 12 seconds after the Big Bang, I'm going to call Big Bang as BB, okay, right? 10 to the power minus 12 seconds after the Big Bang, right? Neutrons were born. Neutrons were born. How exactly, we don't care about it, but the key understanding is that by now the temperature of the temperature of the universe, which was measured to be 10 to the power 32 Kelvin, at the beginning of not measured, which was calculated to be 10 to the power 32 Kelvin at the beginning of the Big Bang, cooled down significantly to about 10 to the power 15 Kelvin. Right? So the neutrons were born first, okay, right? And once the neutrons were formed, subsequently electrons and protons were formed from neutrons, from around 10 to the power minus 12 to 10 to the power minus 2 seconds, and the temperature being approximately 10 to the power 11 Kelvin, right? Please understand this, okay, right? So please understand that the neutron was first formed, and then from the neutron we have electrons and protons. And what I did not address is equally important as what I do teach in this course, okay? What I did not address is how the neutrons were formed, because that's a very ongoing area of activity in high energy particle physics, way beyond the scope of this class. Please be clear about that, okay? So we understand that the electrons and protons were formed from neutrons, and here is the what is the chemical equation representing it? Let's call a neutron, right, having a mass number of 1 and a charge of 0, and that gets converted to the formation of a proton, and the proton is represented by the hydrogen atom nucleus, correct? we have all studied this in high school, okay? Plus electron, whose charge is -1, right? And whose mass is what? Whose mass, electron is supposed to be, it's considered to be a very tiny particle whose mass is negligibly small, okay, right? So with respect to 1, I'm not saying that in this equation, I'm not saying that the mass of electron is 0, but with respect to 1, it is extremely low. That is what I'm representing here. So this is the equation. And as soon as you see an equation, what should come to your mind? As soon as you look into any equation, a chemical equation, what should come to your mind? You should have the balancing of what? Charge and mass. Okay, we need to be having mass and charge as both to be balanced. Is the charge balanced here? The net charge. So this is the charge and this is the mass. Now, so the mass of so the charge is balanced here, 0, and here it's 1 and it's -1. So 1 minus 1 is 0. But what about the mass? The mass is not balanced, right? Yes. So that is why, according to the standard model of cosmology, along with the formation of proton and electron from a neutron, you also have what is called as an anti-neutrino. Okay, right? So the anti-neutrino is also formed, and this is ensuring, this anti-neutrino ensures that in this equation we have both charge balance as well as mass balance. All right? Are we clear about how exactly an electron and proton together form from a neutron? It is through this process. And the key point to remember here is that an anti-neutrino is also formed for the sake of mass balance. So with this understanding, we have approximately like at 10 to the power minus 2 seconds after the Big Bang, and the temperature has cooled down from 10 to the power 32 to approximately 10 to the power 11 Kelvin. And we already have the formation of neutrons, electrons and protons. Along with neutrons, electrons and protons, subsequently, what else can be formed? And by the way, this should be page number 9. And so this is page number 10. So we all know that once a proton is formed, okay, right? What is this? This is proton. This is proton, which has a charge of 1, and it also has the mass number to be 1, which represents the number of neutrons here. Correct? Yeah. So the proton is nothing but is the hydrogen nucleus, correct? Hydrogen atom nucleus. Am I missing something here? Am I being a bit less precise here? What is that I'm missing here? What I'm missing here is to add what isotope of hydrogen I'm talking about. This is again from our current knowledge of chemistry, right? Current high school knowledge of chemistry. We know that hydrogen has 3 isotopes. Now, the proton corresponds to the 1H1 isotope. Okay, right? When I say 1H1, I'm talking about the mass number being 1 and the atomic number being 1. So in general, right, just a brief detour, please understand that the nomenclature to understand isotopes is as follows. I have something like X atom, Y, I'll put element, Y, where Y is the number of electrons and X is number of protons plus neutrons, which is what we call as its mass number also. All right. So in the formation of the proton itself, the proton is the hydrogen nucleus, and this isotope is called as hydrogen. Okay. But what are the other isotopes of hydrogen that we know from high school? It's deuterium and tritium, right? The other isotopes of hydrogen are, deuterium and tritium, correct? So in this lecture, we have seen how electrons, protons and neutrons are formed after the Big Bang theory. we shall continue in the next lecture as to how the other isotopes of hydrogen are formed, right? And also continue how the bigger elements, helium, and the scope of chemistry they present in astrochemistry. Thank you.